So, Kalispera. Good morning, good evening, good afternoon, everybody, wherever you might be. It is my great pleasure to welcome Dimitris. He is from IMPAN, and he will tell us about quantum isometry groups and of Log-Laplacians on Cuntz-Krieger algebras. It's all yours. Take it away.
Thank you for the kind introduction and for the invitation. It's always a great pleasure to give a talk at this seminar. So I changed it here. Okay, thank you. Yes. So today's talk, well, last year I gave a talk about Laplacians and how can one use them. First, how can one extend them to metric measure spaces, and then use them in the framework of noncommutative geometry to build spectral triples on dynamical systems like hyperbolic group bound reactions or fractals or Kleinian limit sets of Kleinian groups, or on Cuntz-Krieger algebras. And today I'm going to talk about work done jointly with here, Amaury Freslon.
From France, right?
From France. And Adam Skalski from here, from IMPAN. Where we study not just the isometry groups, so those spectral triples on Cuntz-Krieger algebras, which we defined with Magnus Goffeng and Bram Mesland, like 2 years ago, 1 year ago. And we're going to, we studied with Amaury and Adam the quantum symmetries, in particular the ones that preserve the structure, differential structure of those spectral triples on the Cuntz-Krieger algebras. And we end up getting like new quantum groups that are very canonical. And also as a byproduct, and in fact we were not aiming for that first, we ended up getting ergodic actions of quantum matrix, compact matrix quantum groups on the Cantor set, and that was not known. Okay. So if I do not erase here,
it will stay, but no, next slide it will be, yeah.
Next slide
will be free of it. So
okay. Yes. Okay. Well, I have to erase. Okay. So I don't have many slides, which means I invite you for many questions. All right. Now, feels, I'm giving a talk about quantum groups to experts on quantum groups. I'm not an expert on quantum groups, but here we go, in case that someone is not familiar with that framework. So, as I said, in noncommutative geometry, we build spectral triples. And so we can make sense of noncommutative manifolds, okay? So typical examples are the actual Riemannian manifolds. And we can also have like actual non-commutative manifolds like the Cuntz-Krieger algebras with those spectral triples that I will.
Why would you call Cuntz-Krieger algebras manifolds?
So, yeah, I mean that's a game with the with the spectral triples.
Okay, so in that sense, I buy it.
Yes, with the spectral triples, and then it is meaningful to study the symmetries or the symmetries that preserve additional structure on those non-commutative manifolds. And to me, at least, it is quite interesting because we kind of understand what symmetries mean on an actual space, divided manifold, and it looks like the symmetries for the Cuntz-Krieger algebras are very different, okay, as they should be because you have this underlying counter space, okay, and the dynamics on it. But I found this project quite fascinating. So here it is, how to study symmetries of quantum spaces of Caesar algebras. So we consider a unital Caesar algebra A together with a core product that goes from A to A tensor with itself, so that it satisfies a co-associativity property, which is this one here. And we also try to make sense of inversion, but it's kind of difficult in that abstract setting. And so we make sense of cancellation. Why is that enough? So here's this is somehow a dual formulation of what a group is. In the sense that if you start with a compact group G, then you consider the continuous functions in G. And on it, you can define the following co-multiplication. So you take a function f on G, and then you define the function on two variables, G1 and G2, and then you just multiply. Okay. So that's the co-multiplication, and you can check satisfies the coassociativity and the cancellation. But conversely, suppose that you start with such a compact quantum group that A is commutative, then you can use Gelfand duality to get a space, okay? And now the definition of being a compact quantum group says that G is therefore a compact symmetric group with cancellation, and therefore it's a group. So you have to go through that to make sense of inversion. And so this is the generalization of groups. And well, the way I view this generalization is to make a theory, to create a theory where you can have self-Pontryagin duality. You know, if you take an abelian, where should I look? Where? Yeah. So you know, when you take a local compact abelian group, then you can make sense of its Pontryagin dual. But if you drop abelianness, the dual will probably not be a group itself. But if you go to the context of quantum groups, then you're fine. So that's beautiful. It's just the right generalization of having this self-dual. Well, a framework closed under dual. Anyways, yes, but then you also have other QT formation, so on, that these probably go to a different direction. And now, if you have a quantum group, then it's sensible to let it act on Caesar algebras. And so we start with that compact quantum group, and B is the Caesar algebra that we act on it. And then, I mean, in this talk, I will focus on left actions. I should say coactions, but coaction is an action. Okay? And
All depends on what you are using. Is a coaction of a sister algebra an action of a quantum?
yes, exactly. Exactly. And we have these two properties that again is associativity minus this constellation part. And so the
Do you mind
first
saying what it
example.
means classically?
Yes, yes. I was about to say that, in fact. But before doing that, I would say that the example that you can just see from this slide of an action is a quantum group acting on itself. Okay? Because you can take this commutative and it satisfies these two properties. So it acts on itself. Now, classically, you can have a compact group action on a sister algebra, and then maybe I just write it here, and then you have. Oops, I want to do it with my hands. So you take that's a group now, okay? And then you view these as continuous functions on the group with coefficients in the sister algebra. Okay, that's the sister algebra itself. And the action is the following. You send these, so you want to send this alpha b to a function on G. So you send it to the function G that does this. Where alpha G is the actual homomorphism on B. Okay. And in fact, if you have sets, then you can just get a collection as well. Okay. So it's an honest generalization of the group actions, complex group actions. And now, one can make sense of the category of compact quantum.
Wait, but how about condition 2?
What do you mean?
Can you explain its meaning classically when both sister algebras are commuted?
Well, sister algebra should be.
Yeah. B to be C of X and A C of G. What does it mean that you have this tense?
That you act with homomorphisms.
No, this is a published condition. It means that the neutral element has spirated.
Okay. Yes.
But it's important. I mean, it's
Yes. No, it's not obvious.
And the reason why we do it is because when you go to the sister algebras of compact quantum, it's not just whole algebras. You might have simple sister algebras, like reduced sister algebra of a free group on reduced convolution sister algebra of a free group on two elements. It's a simple sister algebra, so it cannot have a co-unit.
Yes.
And this is why you have to have this condition. This is what Botnish put down.
Yes.
So, Piotr,
Yes.
sorry to interrupt, but I think there is a problem with sound. Is like there is an interference. It's crackling. There is a lot of noise.
It's strange because we have microphones next Okay, guys, can you hear us now?
Yes.
You see, internet collapsed at IMPAN. The whole
Yeah.
Eduroam collapsed totally. So this is why we had problems hearing us. It wasn't microphones. It was internet because
Okay.
it collapsed on all the computers and on all phones.
Okay. But it is also so possible since you have a microphone in your shirt, right?
Yes.
Maybe it is close to your smartphone and that's the interference because we can still hear it.
Okay, so maybe so what?
Yeah, we put it back.
But okay, my smartphone is in flight mode, so is it still
Okay.
interference?
Okay, so maybe it's just still internet that is not optimal, but it's fine. We can understand, I think. It's fine.
Now can you hear me cleanly?
Yes.
Okay.
Wait, this is we are connected. So what's okay? All I have to do is to share screen.
Please open this isometries of one.
It's
Yes, it's here.
Okay, now we should see it. And let me make it. No, it's already full screen. Okay. Sorry for this interruption, but I really have no control. All of a sudden, internet collapsed all over IMPAN. So sorry.
Thank you for your patience. Okay, and an object we are also interested into the category of quantum groups that act on a fixed system algebra, and in particular, in the existence of a universal object through which all compact quantum group actions factor. And by that, I mean we want we focus on the sister algebra. That's a compact group action, and we look at the universal object, and through which the actions factor. And we also want this map to come from a map like a homomorphism that respects the co-multiplication.
So in the sense of the coactions, it's
Yes.
it's initial.
Yes. But in the sense of the groups, it is final. So that's why I put it final.
And how do you know it exists?
I will talk about that. Yes. But these are issues that show up in the quantum world, the existence. Exactly. So please ask any questions. Okay.
So for this existence, are you assuming some additional properties of this section?
On this slide, and for now, no. But I'm not claiming it exists.
So for final dimensional,
I will talk about yes. We'll talk about. But let's see a few examples that are closer to today's talk. And let's start with the symmetries of the endpoint set. So consider the category of compact public groups that act on C to the n. And this, that was the theorem of Wong in 1980s, admits a universal object that is denoted by Sn plus, and it's a quantum version of the permutation group on any points. And its sister algebra is generated by projections where the indices I and j, they are between 1 and n. So you want the projections, and then you want the matrix P here to be limited. Okay. Now, this is a magic unitary in the sense that except for all the entries of the matrix P are doing projections, and we also have that the rows and columns are mapped to 1. Okay, so it's like a stochastic matrix, stochastic, and so yes, and the multiplication of this quantum group, it's really, the matrix multiplication, and it's easy to check. And the action of this quantum group on C to the n is again matrix multiplication. Yes. And so one can then make sense of quantum automorphism groups of graphs. So we consider the adjacency matrix of such a graph, and you denote it by A. And then
the same notation as for your quantum group sister algebra before.
Yeah.
Is it bad?
I'm not gonna use A again later on. So at this slide, yeah, that's a good point. Probably we denoted that with M. So the quantum automorphism group as a sister algebra is again generated by massive unitary. Since all the entries are projections, and then you ask for this additional relation, you want it to commute with the adjacency matrix A. Of course, if the adjacency matrix A has bases, or then you end up getting the permutation group. Now,
May I have a question?
of course.
If you remember, the problem of the existence of this universal correction is in this finite dimensional case, for Cn at least, is related to the fact that this correction preserves this counting measure of finite set.
Yes. It's in the next slide.
Yeah. So in general, you can assume preservation of some faithful measure on the algebra like Teton, Cox Teton, and then you also obtain this universal property. But then I'm thinking about this directed graph case. Do you have here some functional which is preserved under this correction?
Next slide.
And universal answer. Next.
Next slide. These are very good questions, but I was prepared. So.
And we're just making a preemptive strike.
Exactly. So one thing to note is that the quantum permutation group for any equals 2 or is classical. So it always contains the classical group, and then people, like, for many years, there's also a lot of reasons modern work on determining how much different the quantum automorphism group of a graph is from its classical version. And I think it was very recently, like November, December of 25, like 12 months ago, that was it Brown, Robertson, and Schmidt, I think. They gave the first example of a graph with trivial automorphism group and non-trivial quantum group. That was not known. So although it's a very digestible definition, it hides a lot of complexity. Okay, and let's see. So, as Tomasz mentioned, the category in a finite dimensional, well, I could just put here a finite dimensional algebra, but I just want to keep the notation simple. So if you think the n by n matrices, this algebra, then this does not admit a universal object, while you actually think of matrices and not just numbers. And so I haven't really checked the proof of why this is happening, but I think I understand why this is happening for 2x2 matrices. The thing is that every compact quantum group action in a finite dimensional algebra, like on MN, preserves a faithful state. And so if you had a universal object, then that universal object would preserve a faithful state, which means all the other groups acting on MN preserve that given universal state, that state of the universal object. And so on 2x2 matrices, I think that was Piotr Zoltan that constructed, correct me if I'm wrong, but constructed actions on 2x2 matrices and also different, like two groups that act differently and they preserve different faithful states, but the actions are also ergodic and those are unique. And so you cannot have that every two quantum groups that act on MN, they share a common invariant state, which you would get if you had a universal object.
Nice, I found
so I think not from that. Okay, but if you preserve the state on MN, and all the states are S-bar, or you take a density matrix, then you cannot do this argument that I did because you just focus on one state, and one can show that you do obtain the universal object, you know, this final object that everything factors through it. And the situation for Gerontogiannis algebras, whether you have a universal object, like quantum symmetries, or algebras as we studied for by several people, like Vanica, Skalski. And yes, as I said, today we will focus on Cuntz-Krieger algebras and quantum symmetries that preserve additional structure, okay? Because
question about this faithful trace implemented by this density matrix. You could take identity divided by dimension matrices, okay, and then you obtain not only the faithful state but tracial faithful state.
Mm-hmm.
So, do these universal objects preserving this universal tracial faithful states somehow distinguished among these?
Well, if they are different.
Yeah.
That I don't know. But probably one can figure this out because it's an algebraic. So algebraically, probably one can figure this out. But on the top of my head, I don't know.
So
maybe you could pick up the difference.
So I'm looking at this algebra with this state as some kind of a distribution. So if you have this equally distributed probability 1
Yes.
over n,
Yes.
this case is more symmetric
Yes, of
than
course.
some arbitrary
Of course.
density matrix which is concentrated
Of
at
course.
one place and
Yes. Of course.
zeros outside.
Yeah, I don't know the relation between them for different choices, but that's a good point. In fact, try to think about it. Probably people know, someone knows, but it's a good question.
my question to the two of you is, so preservation of this counting measure is automatic when you look at CN. It's automatic because you never assumed it.
Yes. because it's an action of a compact quantum group. You can forget about this condition, and then you obtain the universal action of a Hopf algebra, which even for n equal to 2 is different from classical permutations.
So they are saying that you have this automaticity because it's a compact quantum group, not just a Hopf algebra.
Even less. If you have of course, this reduces to the correction of this dense star subalgebra,
which is cosemicism.
Which is cosemicidity. Cosemicidity is according to Bishop, I remember well. Crucial.
And this would entail that this counting measure is automatically preserved. But if you go to beyond cosmic simplicity, you must assume something in order to have a universal object.
Yes.
Happy. Thank you.
And
also commutativity is important.
Oh yes.
Because now you have an example.
No.
Example.
Commutativity, of course, I know.
And so, as I mentioned, we care about the symmetries of additional structure on the sister algebra. And like what was initiated by Goswami, Bhowmik, and several, I mean, I would have put a slide just with names here. Apologize for not putting all the names. And several collaborators in 2009, roughly, that they studied quantum symmetries, called quantum isometries of non-commutative manifolds, and by that I mean he wants to preserve the structure of a spectral triple. And I guess everyone's familiar with a spectral triple here, but just for completeness, the spectral triple over sister algebra B is a triple of data where where B is represented as multiple operators on a Hilbert space. Mathcal B is a dense star subalgebra of B, and D is a self-adjoint operator with compact resolvent, so that the operators in this dense algebra they preserve the domain of the maximal domain of the operator T, and then the commutator here tends to a bounded operator on H. So this is a triple, and you can think of the Dirac operator on the manifold, spin C manifold, and D is the differentiable function. So then we focus on quantum symmetries of P, like the ones I just described, that commutes, and I will make this more precise later on, with the operator D. And then the question still is there a universal object? Now, such a universal object, if it exists, we call it quantum isometry group. And a deep result of Goswami and Jordan of 2018 asserts that connected closed Riemannian manifolds are called classical isometries. So there is a universal object, and it's as small as it can be.
So you assume
from the quantum perspective.
But you assume connectedness, because otherwise you have quantum permutations of
Exactly. But I think that's a deep result. It's very enlightening. And today I'm gonna give you an example of a non-commutative manifold. That this is by far not true.
May I have a question? In this non-commutative case, you can always add a self-adjoint element in the algebra.
The non-commutative case you can
to D, or representation of the self-adjoint element to D.
Yeah.
So
D plus something.
Yeah. So as a derivation for the commutative thing, it acts trivial. But maybe this can modify this Dirac operator non-trivially in the non-commutative case. And then there is a question of what happens to this universal symmetry object when you deform your Dirac by adding the image under this representation of some self-adjoint element in the algebra itself.
Yes, yes, yes.
So
I don't know. I don't know how this would affect in general. You mean like unbounded? General.
Yes. You're adding a bounded
Bounded.
element of the algebra under this
Of the
representation.
algebra. So you
Yes,
are.
it goes to the bounded operator. So if the algebra is commutative, then this derivation, this commutator, is unchanged.
Yes.
Okay.
Yes.
But
Yeah, if
for
we could add more,
non-commutative, maybe it could change this universal symmetry object.
could be.
So I wonder how.
Yeah, it's a quite complicated subject, I would say. But it's also a good question. Now, some question that I have to you and to the audience is the following. So, classically, we know that every group is the isometric group of a connected, locally connected, complete metric space. In particular, every compactly group is a isometric group of a closed connected Riemann manifolds. To what extent can we go quantum here? So, yeah, I would really like to know this answer, the answer to this question. But I don't know, but I'm curious.
Can you remind me what locally connected means?
It's not important here. I mean, locally it's connected.
I mean, I'm just wondering if something is connected, is it automatically locally connected or not?
So, in particular here, this is one-dimensional. You can view this as everything as being one-dimensional. So, you can think of spaces like so something that you would not have in it would be some attractors like dyadic solenoids. You wouldn't have it in there, but you have like other connected spaces.
But I'm asking, if something is connected, does it imply that it's also locally connected? No. That's a pretty connected.
So this is probably the difference between discrete spaces and
Yes.
and dyadic spaces.
Yes.
Okay.
That's why I said that dyadic stuff. Anyways, so I'm going to do a quick recap on the spectral triples on Cuntz-Krieger algebras. And yeah, we have time. So let's start from the basics.
So what's a primitive matrix?
I will explain everything. So take a primitive matrix. So a matrix is, we focus on matrices with entries 0 and 1 here. Primitive means that there is a power of A, so that all the entries become strictly positive. So you don't have any 0 in it. Now, such a matrix, you can view it as the adjacency matrix of some finite directed graph. And by saying it is primitive, it means the graph is strongly connected and it's not a permutation.
So it's a generic property.
It's not a sign.
It's a generic.
It's a
generic property.
Yes.
And by strongly connected, you mean that between any two vertices, there is a directed path which connects the two vertices.
That's the connected. There is
no connected is when it's undirected path.
No. Strongly connected means there is this number k that you take the positive. It means that any two vertices can be connected by a path of length at least k.
Yeah, but it's a directed path.
Yeah, it's directed.
Yeah, but connected means that it's undirected.
Sure.
Yeah, but strong means.
Yeah, this is what I'm asking.
Yes. Well, strong means that you can connect everything in a very nice way.
That's exactly what I said. I mean, that strongness means that this path is directed.
Yes. And so, as soon as you have such a graph, you can think of the space of infinite paths. And equivalently, since you just have up to one edge between two vertices, you can view it as infinite words, one-sided infinite words, where the letters are numbers like 1, 2, and up to n, okay? The labels of the verses. And the adjacency matrix dictates when you can concatenate, when you can continue the path. Now, this can be turned into a compact Hausdorff space. You take the discrete topology here, then the product topology, so it becomes compact. And this is a compact subset of this counter set here. And so you can also put a natural metric on this space, dA. So the metric really you take two paths and you see for how long they are the same. On the first moment, they become different. You keep that number, and then you say x, that the distance is, let's say, 2, the minus that number. Okay. Now, if they're just the same, it's infinite, so it's 0.
Can you tell me what TMC stands for?
TM, set topological path of chain. Yes.
Okay.
And then we also have the left shift map on here, so shift to the left, and that's a local homeomorphism. It's not injective because you could have, I think it's clear, it's not injective. And an important element for what we want to do is the conformal measure on this metric space. So how do you contract this measure? This comes from the Venus theory. And doing the following. So your matrix A is primitive, and the Cuntz-Krieger theorem says that you have a distinguished eigenvalue greater than 1 in this setting, that all the other eigenvalues of the matrix A have modulus strictly smaller than this distinguished eigenvalue that let's denote by lambda A. And then this eigenvalue is simple, so the eigenspace is one-dimensional, and so you can consider an eigenvector like that, but you normalize it so that the sum will be equal to 1. Also, this eigenvector has something very interesting. All the entries are strictly positive.
This vector?
Yes.
This vector. Probably distribution.
Yes, exactly. Now, you can do the same for the transpose A, and you end up getting another vector, B. And you can normalize B so that it is equal to 1. Okay? That's too much. Bi, ui. Okay? So that it is equal to 1. And now, this also gives you a probability distribution. And you can call this PI. So it's a distribution on the vertices. And now you can define a measure on this space by putting a measure of the so-called symmetry sets. So the basis for the topology here is given by sets where you prefix the left tail, the start of the paths. So you could think of sets, for instance, starting with some word alpha 1, alpha 2, alpha n. Okay? So all the paths that they start with that, and then they can be whatever, they are in there, and this is a Kloppen set. And you put a measure on the space by putting so we take the probability of starting at the first vertex, and then multiply and continue below with the probability of jumping from the vertex alpha 1 to alpha 2, and then jumping from alpha 2 to alpha 3 up to the probability of going from alpha n minus 1 to alpha n. And what are these transition probabilities? They are given by this data. So maybe I just, for alpha and beta, maybe I just write by j. It's so first of all, you want I to be able to go to j, and then you put j over lambda a u pi. Okay, and this defines the transition probability of jumping, and you can see that this is a Borel measure here. And this is not the Patterson-Sampan measure yet, so this is invariant under shifting. I mean, you can do stuff I won't prove this here, but there is a conformal version of that, and which is basically so conformal version of that is the following. What's the fastest way?
By conformal, you mean
yes.
This measure is quasi invariant.
Yes. So what I mean is that you come up with
after some car.
Yeah. So if you take if you shift by some k, where k is smaller than or equal to n, and you take this up to n. So you take the center set and you shift it. This is going to be lambda a to the k of and a of the measure of the symmetry set. Okay, so you need this conformality. The first measure does not have it, but there is a natural way to go from the first to the second. And this is also the solution to the Perron transfer operator. So there's a lot of dynamics going on here. But this is the measure that we care about. So probably I should have written like mu a here and mu a here, because it's the one that we want. And this is options on one. And
excuse me, is there a relation between this
yes,
the measure and
they are
metric?
Yes, they are absolutely continuous, and there is a relation between the measure and the metric. Very well. So any ball of radius r, where r can be like 2 to the minus something, every measure, every ball of radius r has volume r to some delta, and that delta is the Hausdorff dimension. which is given as basically the logarithm of this number. Now, that's the dynamical data we want, and now jumping to Cuntz-Krieger algebras, I guess almost everyone knows about these. So you consider n operators as I turn out into these relations to be partial isometries. So you want the range projections to sum up to the identity. Also, you want Si star as k, if k is different than I, to be 0. And source projections, Si star Si, to be written in terms of the range projections associated to vertices, to which one can go if they are on I. Also,
so this could be a series or
No,
it's
finite.
It's the size of a matrix.
Yes,
okay.
Everything is finite.
Okay. It's a very simple
Yes.
graph. You have finitely many vertices. You don't have any infinite emitters.
Yes.
You're finite. And basically, I mean, because you assume that the edges are 0, 1, okay? So basically, so also you have no repeated edges,
Yes.
right?
Yes.
So this is a very simple graph. Now, I'm wondering, can you have sinks here? No, probably not, because even the column would be 0.
DDT,
Which is close sinks.
Sinks, yes. So we are
So-called regular graphs.
no,
Finite regular graphs.
so they don't need to be regular in the sense that the in or out degrees are the same. Every vertex.
Regular just means that every vertex is regular.
Yeah, but
And
not.
if you have no sink and no
Yeah, sure,
regular
sure.
graph.
Yeah, but there's also the notion of having the same in or out degree at every vertex.
Different than regularity.
Yes, that's different notion of regular.
This is called regularity.
Yes. So, yeah, there this situation, it's a nice graph that gives rise to a chaotic dynamical system because the entropy is positive, and you also have densely many periodic points. So,
Oh my God.
sorry, what kind of entropy? Topological entropy.
Topological entropy.
Yes. Okay, so that's the Cuntz-Krieger algebra, and in order to describe the symmetries, well, to put a spectral triple on it, we wanted more. This is joint work with Bram Neslan and Markus Goffing, and we wanted to have a more geometric description of the Cuntz-Krieger algebras. So we pass to the Renault-Voigt picture, which means we consider this groupoid here, and well, I think a good way to look at it to understand this groupoid is the following. First, you put n equal to 0. Okay, you put this equal to 0, and then what you end up getting is tail equivalence. So you consider infinite words x and y, so that they're tail equivalent. They are the same after some point. On the right, you look at them. So you shift enough, they become the same. Now, if you introduce this integer n, then you'll have some lag. So it's a weaker notion. Now, the multiplication, the partial multiplication of the groupoid is as follows. So, as usual, you can multiply whenever the source of this triple, which is y, is coincides with the range of this triple, and then you also add the integers, the lines. Now you can put an étale structure, like the range of source or local homomorphisms. Of course, the unit here is, x, 0x, the triples, which is a shift space. And the basis for the topology of the groupoid is simply given by looking at open neighborhoods of X dictated by some finite word alpha, and open neighborhoods of Y dictated by some finite word beta, so that if you shift by alpha, by the length of alpha and beta, X and Y become the same. Now, OA, then, the universal version of the Cuntz-Krieger algebra, is canonically isomorphic to the groupoid sister algebra. And the assignment is the following. You consider the characteristic function of the groupoid of this set here. So x1 and the shift of x. And it's a groupoid, so we can make sense of convolution. And therefore, we can make sense of this convolution operator. And one can show it respects, it satisfies the Cuntz-Krieger relations. But also, and so you have a map, surjective map from OA to the 2 points algebra. But then you can also show that, I mean, the dummy way to do it here, to show the isomorphism, is we use the fact that the matrix is primitive, and so the algebras are simple. But the actual reason why these are isomorphic is because they preserve this isomorphism, this map preserves the gauge actions, respects the gauge actions. So the gauge action on here is the action of the circle, where you send Si to Z, which is a number of modules 1, circle to Z Si. Okay? So this is an automorphism of the circle, and you also have the same action that the point level here. Okay. So this is
can I ask a question? Do you write a reduce the groupoid sister algebra because is non-isomorphic to the full one, or maybe in this case are they the same?
They are isomorphic. The reason I write the reduce is because this is really the one that is generated by these convolution operators.
Okay, thanks.
So it's the one that gives the more geometric, but the groupoids are amenable, so the full and the reduced are isomorphic. Okay, any other question?
So usually reduced is related to regular representation.
Yes.
So what is this regular representation here?
What do you mean? I mean, you convolute, so you first need to define the convolution and how you convolute two functions, and then it's the convolution with that function. So you take supported continuous functions on the groupoid. You make sense of the convolution, which is a finite sum. And with the convolution, you can make sense of convolution operators. The Hilbert space here, I mean, you just do what you do in the
kind of L2 of something.
Yes, yes. But it's not very important now. I mean, I also have other stuff. If I start doing this, yes. Now, how do you put geometry on this groupoid? There's a typo. I should have put gamma alpha. So in our work with Magnus and Nessla and Brown, we used the Log-Laplacian on metric measure spaces with a measure that has a nice relation with the metric. These are called Algebras regular measures. And it really has this form, okay? And in particular, these shift spaces, they have this Alfors regular metric measure structure. And therefore, you can make sense of this operator. So F, you can think of the Lipschitz function on the shift space or a locally constant continuous function. And it's defined as follows: you integrate over the shift space the function and you divide by the difference, and you divide by the distance, and you raise the distance at delta, our delta, where delta is the Hausdorff dimension of the shift space. And then you integrate. So this we call this a Log-Laplacian because if here you have a manifold, a closed Riemannian manifold, it's really the logarithm of the Laplace-Beltrami plus a bounded perturbation. And this is what we did with Bram like 2 and 3 years ago. All right. And the idea on how to put, how to lift the Laplacian on the Log-Laplacian from the unit space of the groupoid, which is the shift, was to decompose the groupoid on alpha into 4 index sets. I'll make some index sets. Where these are Kloppen subsets of the groupoid, and on them you can make sense of the Log-Laplacian because they are homeomorphic to cylinder sets in the shift space. So you have the Log-Laplacian, you have a measure, and from that you lift everything up to the groupoid, and this gives a metric and measure of the groupoid. Now, this is a locally compact space, okay? Whereas the shift space is compact, and the Log-Laplacian makes sense on finite measures due to the threshold it has here. If we had an additional positive number, the power of the distance here, it would make sense also on locally compact.
Yeah.
On infinite measures.
Let's assume that we are in the Euclidean space,
Yes.
finite dimensional Euclidean space.
Yes.
And we have the Lebesgue measure,
Yes.
and we have this Euclidean distance.
Yes.
Okay. So that is that the right hand side makes sense. How this integral is related to the Laplacian? So
It's the one with multiplier log psi. So the Laplacian has multiplier psi to the 2 psi squared, whereas the Log-Laplacian has multiplier basically 2 times log psi. Now this is also a non-local operator in the sense that if fx is 0, delta of fx doesn't need to be 0 because that part would be 0. The rest, I mean, you integrate over all the space. Whereas the actual Laplacian is a local operator. Okay. But for now, I don't want to go through that. It's a different topic on its own. It's just that we have these non-local operators, positive, self-adjoint, compact resolvent, and it really does the work in a canonical way on constructing canonical spectral triples from Cuntz-Krieger algebras.
can be this local Laplacian expressed using some functional calculus applied to usual Laplacian?
Yeah, that's a great question. Depends on the space that you start with. So if you have, as I mentioned, closed the Riemannian manifold, then yes, and we proved all this stuff with Brown. It's in the paper. Then you can show it's the logarithm of the Laplace Beltrami plus about perturbations that comes from the heat trace asymptotics and so on. There, you have a Laplacian to take the logarithm of it.
Okay.
On here, though, on a totally disconnected space, you don't have a local operator because it's totally disconnected, and so you can use the characteristic functions to show that you cannot have this locality. It's like you ask for a local diffusion, and on the Euclidean space you can diffuse, but on total disconnected space you get trapped within the cylinder sets because you actually partition the sheet space into sets that they have distance between them. So it would have to jump.
So the Log-Laplacian is the most general notion. And
yes,
sometimes
exactly.
it can be expressed
Yes.
up to some
Yeah, it's more general.
basis.
Yes, exactly.
Okay, I see.
Yes, exactly. Exactly. And also, if you take any other power here, like if you put like some plus alpha, where alpha is between 0 and 1, then you would end up getting something called the fractional Laplacian. But then you wouldn't end up getting spectral triples for Cuntz-Krieger algebras because they are purely infinite, the Cuntz-Krieger algebras. And the fractional Laplacians would lead to finitely summable spectral triples, and you cannot have those. But you can also see it from the proof. So it's like the dotted line is a singular kernel here. It's just like at the right. It's the right kernel, looks like. So we lift all this non-local diffusion from the shift space to the groupoid, and again we end up getting the same expression. But now everything is nice, so almost nice. So if you consider now so you consider OA as the groupoid acting on which is C star alpha, which acts on L2 of this with this measure, which by the way can be identified with L2 of OA with the GNS space of O2 associated to the gauge, the QMS state of the gauge action, canonically identified. So delta action here in this L2 space, it is self-adjoint, positive, but it does not have compact resolvent. The kernel of the is infinite dimensional, so it will not give a spectral triple, even if, which is irrelevant. Yes, so it doesn't give a spectral triple, but we also have that delta in the commutators with the generators of OA, so with a dense subalgebra, the canonical dense subalgebra of OA, they are bounded, they extend to bound operators. So you have almost everything for getting spectral triple except for the compactness of the resolvent, which makes sense because this is a locally compact space. So you cannot expect it to have compact resolvent. But there's a fix, so I will not introduce this potential, but you can make sense of the Hamiltonian alpha. So if you add an unbounded potential, and then this operator D appears to be the right object. So
is this potential canonical?
Yes. Yes. And it's somehow it is a scaling potential, and it looks the level of multi-resolution analysis in the groupoid somehow potential. And then indeed we end up getting the triple of Cuntz-Krieger algebras and the homologies in general non-trivial for those spectral triples. In fact, their K-homology class generates the K-homology of the Cuntz-Krieger algebras, so it's very canonical. And recently, work in progress with Magnus, we studied spectral geometry, heat traces, zeta functions, KMS states from those spectral triple, and we end up getting like very, very geometric and new stuff. But that's different talk. Now, going back to isometry groups, one can make sense having a general spectral triple, but for this specifically, of the isometry group of the spectral triple, and it's defined as follows. So you take any homomorphism on OA, okay, so that it can be implemented by a unitary on here that commutes with the operator D. Okay, this is a group. The implementation is not unique, but as soon as if you have those automorphisms preserve the KMS state, then you can choose the implementation to be the following. So Perl is the representation on here. And psi is the cyclic vector. Okay. And so barring x, where x is in OA and this and you let rho x acting on this cyclic vector, you end up getting a dense subset of the equal space. And so if your automorphism preserves the KMS state, then a canonical unitary implementing phi is the following: rho phi x psi. In fact, this is equivalent to preserving this is unitary if and only if phi preserves the KMS state. Now, an interesting fact is that we don't need to assume KMS preservation here. So if you'd like to take any unitary implementing phi and work out, because you ask for it to commute with D, so it should preserve the finite dimensional eigenspaces of D, so you end up getting algebraic relations. Very soon you realize that such phi has preserved the KMS state, so then you can choose this unit.
Can I ask a stupid question?
Yes.
I'm a bit confused about the notation D. You write D and you say Hamiltonian, so that's, I shouldn't think about it as the Dirac operator in the spectrum.
No. But it has all the it behaves
Laplacian and Dirac.
Yes.
Correct.
Self-adjoint.
Yes, it's self-adjoint. So then we computed with Brown and Magnus that the isometry group is a compactly group and it's the automorphism, so A acting on the end points. And the steps for computing it are the following. So the first eigenspace of this Hamiltonian are really these projections, and the second eigenspace are these partial isometries. And so, just from asking the unitary to preserve those eigenspaces, soon you end up getting that the isometry group should be inside this semi-direct product. And now one can check whether, and then should the morphism should have this form, but not where U defines a unitary matrix, but not all of them give rise to an automorphism of the Cuntz-Krieger algebra. And so there is a way to see exactly which of those actions maps on the Cuntz-Krieger algebra give rise to an automorphism. And then one can see that the isometry group embeds in the group that we're interested, and then one can see that this group, in fact, acts on our algebra and on the groupoid by isometries, also preserving the measure, which is the KMS state, and hence, because we have a Laplacian, okay, if you act by isometries, it commutes with a Laplacian, because we have points there. And this is how one can show this. But now going to quantum.
So you have, among this operator commuting D, you have some unitary of the form e to square root of minus 1 d.
Yes.
Okay. What kind of symmetry is this?
Sorry, come again?
What kind of symmetry is this?
E to the minus square root. I didn't hear the first part of the question.
So e exponent of the imaginary complex number unit times d.
Yes.
So
Actually, it's something that we study with Magnus later on, because you can also define a flow by taking.
So this flow is what?
Next year. Okay, so this joint work with quantum isometries. By the way, Piotr, is it fine if I have like plus 5 minutes?
Well, we still have 10 minutes.
Yes, plus 5?
Oh, yeah, of course.
Okay. And so, I mean, Peterson taking out easy lemmas. And the difference here in the quantum setting is that you have a coaction now, but we figured out that we had to assume to preserve the KMS state. It doesn't come for free as it comes in the classical situation, and for very good reasons that one already can observe algebraically, and also for another deeper reason, but you will have time. Yeah. But this lemma really says how you have an action of a compact quantum group on OA. How can it be implemented by a unitary? Okay, and this is what one expects. So you have this action, and you aspirate to preserve the KMS state, which is exactly this condition here.
So, are you telling that when you have a Cuntz-Krieger algebra, you have a canonical KMS state, or do you choose?
Yeah, for the gauge action.
For gauge action.
For the gauge action, yes. And otherwise you can have exactly. And now the idea is the following: that you consider this Hilbert module. So you view this as a right Hilbert CG module. One could, of course, put them, flipped to actually look like a right one. But then, in the quantum groups that we get, we would have to flip the multiplication inside. So it's an aesthetic choice to view this as a right Hilbert module of CG inner product. And now this really tells us how to define a linear map that extends to a unitary on this Hilbert module that implements, in this sense, the action, as I wrote before. Before I had written that the action. It's not here. That the action. That the unitary implements this automorphism that acts on OA by really passing the automorphism inside. By shifting, basically, by the automorphism, so you can do the same if you assume the KMS preservation at the group level. Okay? And the definition we're using, which is basically the one that is used all over the place, but the fact that Cuntz-Krieger algebras are nice, and also the operator D is very compatible with the Cuntz-Krieger algebras, we can give it cleanly without involving multiplier algebras, so on, using these three bullet points. So an action, a coaction of a quantum group on OA, we call it D-isometry, it preserves the data sets and preserves the domain of one tensor D, the one factor term this part, and also commutes with one tensor D. Okay, so this one's we have. And now you consider the category of the quantum groups acting on OA, which are these actions D-isometric. And then you look for a universal object. And if it exists, it's going to be unique. And this is what you call the quantum isometry group of OA. Okay, so I described all this stuff at the beginning, so and move on. Yeah, another lemma, but it's kind of interesting. So a nice thing about this Hamiltonian D on Cuntz-Krieger algebras is the following fact. Its eigenfunctions are some sort, at the groupoid level, of course, of hard wavelets. Like functions that integrates to zero, they give a basis, normal basis, so on and so forth. It's like the e to the I and x that you have in the circle. These are the eigenfunctions. And they span the dense subalgebra generated by the generators of the Cuntz-Krieger algebra. By this, I mean all the locally constant continuous functions on the groupoid, which is exactly the, so that's not the C star, that's C. There's C star, and you have the generators. Okay, so you have polynomials on the generators of the Cuntz-Krieger algebra. And so the wavelets span this algebra, which means we take a compact group, a compact quantum group, which D acts D isometrically, so it commutes with one tensor D. Then, if you focus on these functions on this subspace, so this is also a core for the operator D, then it will get preserved if you focus on the Hopf subalgebra. The reason is that D has compact resolvent, and so all the eigenspaces are finite dimensional. So if you ask for the previous unitary that I showed on the Hilbert module to commute with one tensor D, it means that it preserves those finite dimensional eigenspaces. So it preserves, let's say, GG tensor, the first eigenspace, because usually commutes with one tensor D, for instance. And so this is a unitary representation of the quantum group. Okay, and so that's why you also end up getting this subalgebras coefficients. And then this allows you to make sense, to write nicely the adjoints of this unitary, because it involves the antipode, which we haven't assumed any Katz condition. So it would create many complications, but the framework is such that you can work with K inverse, and then just
SI here.
SI.
Yeah. C star of SI, you wrote it in.
It's the polynomials, the span of SI and its inverse. It's the generators, of the Cuntz-Krieger algebra.
Okay, so just want to double check that these are the
Yes.
isometry.
Yes.
And how can you say inverses?
Inverses?
Did you say inverses?
No.
No.
Okay, I heard inverses. Okay.
No. There are joints.
Joints, yeah, fine.
Yes.
Did
Did I say
inverses?
inverses?
Inverses.
Okay, I meant that joints. Yes. So, no, they're not
Okay,
invertible.
check the record.
Yes.
Okay.
Exactly. The cameras. Anyways, so, and long story short, we came up.
It's a very Greek name.
Yes. That's a good reason. Long story short, maybe I should go to this picture again. So the game is really the following. You try to come up. First, you take a compact quantum group acting the isometry, which means commute with one tensor T. And then you try to derive as many algebraic relations you can, so that you end up getting unitary representations and build a quantum group. Okay? Then you ask yourself, does this quantum group act diametrically? And that's you come up with. It might, so you're in a good position, but it might not. Okay? So if it might, then if it doesn't act isometrically, then you need to derive more algebraic relations to make it smaller. Okay, so it does act isometrically. Now, if yes, but then you shouldn't dig, too much in the structure because you also want it to be the biggest object through which all the diametric actions factor. So it's a tricky game to play. And long story short, we ended up with these groups. And so you consider the universal system algebra generated by partial isometries, so that the range in source projections, they form matrices P and Q. They are both unitaries, the massive unitaries, and you also want them to preserve the Perron-Frobenius eigenvector, the one that I showed before. So these are matrices and eigenmatrices. So if they act on the Perron-Frobenius, they have to preserve it. You also want P and Q, A, which is matrix linear line P and Q. And already this condition shows very much resembles the quantum automorphism groups of graphs. But here the difference is that P and Q can be different.
So what is this dA to the power n?
dA.
Yeah, condition 3.
I will explain. But this can be different. For instance, for the Cuntz algebra, A, where A has only one entries, the condition 2 is automatically satisfied because P and Q.
But we imagine that this is not a 0-1 matrix.
It is a 0-1 matrix. You mean?
You said Cuntz algebra.
If you are in the setting of the Cuntz algebra,
yeah,
then all the matrix has only aces. We think of that once.
Because you are using different graphs.
Yes. Yes. Yes.
Okay. Mm-hmm.
And then condition 3 says the following. If L is equal to 1, then it doesn't say much because it asks for, you take products, and these are the allowable paths, the allowable words that you can make of length n. So if L is equal to 1, then you just ask these to be partial isometry, but this is already assumed. But if L is larger than 1, let's say 2, then you ask for the product of those partial isometries whenever under indices you can create words to be partial isometries. Now this is not always true. The product of the partial isometries is a partial isometry if and only if the source projection of the first commutes with the range projection of the second. So this is a commutativity condition. And then, indeed, this gives the quantum isomorphism isometry group. In particular, for any L, where L can also be chosen to be infinite. Okay, so if you put here infinity. Okay, so for every L, these quantum groups, they act on the Cuntz-Krieger algebra. But only for L equal to infinity, they preserve the KMS state and they act de-isometrically. Also, as quantum groups, you have that G1 is smaller than G2 or equal G3 and so on than G infinity. Okay, so you get this sequence of groups. And only if you go down to infinity, which means you ask for all those products of arbitrary length to be partial isometries, you end up getting.
So G1 is the biggest.
It's the biggest. Because you ask for less.
Ah, okay.
And
so L is the length of the Ariadne thread.
Yes.
Okay.
Exactly. And why thread? Because you need to go to infinity or to the right point to find the isometry group. And in fact, it's more involved.
Wait, but because the line from line said it's impossible to.
Yes. But here are some properties. So the first one, the big one, contains the quantum automorphism of the quantum automorphism of A, where the infinity one can so it contains the classical automorphism group. Okay. So from the automorphism, the graph automorphisms, it's not that large. Now, another thing is that all of them, and in particular the infinity one, contains the dual of the free group. So it's always non-trivial and purely quantum. Another one is that, and that's I find philosophically interesting, is that the Abelianizations of all these, they give the classical isometry group. So if we go back here, the G1 really shows up by asking the action to commute with the truncated version of the Dirac, of the Hamiltonian, quantum tensor D, on the first eigenspace by asking to preserve the first eigenspace. This gives G1. If you ask it to preserve the first and the second, this gives the smaller G2. And if you ask it to preserve all the spectrum, all the data, you go to G infinity. But the classical versions give the same group, the isometry group, the classical isometry group. So it means that going quantum, you really see like different behavior and different symmetries. And yes, and you have to have access to all the spectrum.
So G1 is also symmetrical?
Of the truncation of the first eigenspace.
G infinity.
It's all, yes. G infinity is the isometry.
That's the smallest.
Yes. But here's the interesting part. So, yes, by the way, for the full sheets, these groups, we found out that they can be identified with easy quantum groups, like defined partitions, and they appeared recently in Mann's thesis, generated a slightly different way. And from also his work there, we end up getting that Ariadne's thread for the full shift doesn't stabilize. Never. So all these groups are different. Whereas, now if you take this, for the Fibonacci shift, which is this matrix, A equals 1, 1, 1, 0, it stabilizes at step 1. So all the groups are the same. So you end up getting different behavior depending on the matrix A, and this is something that we don't understand yet. And also, it says, we also show that like for the full shifts, that this is a quite large quantum group still, because it has a subalgebra which surjects onto this the product of two quantum permutation groups, and this means it is quite large still. And finally, we get the following. These are not just the quantum isometry groups, and which is fine, it's nice, but those they act logically on ON, like for the full shifts. Like for the Fibonacci one, they cannot act ergodically, because for the Fibonacci one, here, this, well, all the GLs are just the dual of the free group. So it can be, they are as small as they can be, because they contain that. For every L, for the Fibonacci. Whereas for the full shift, they are all different and much bigger than that. And then the following interesting thing happens, that this action of the quantum isometry group on ON, it also preserves the massa, the diagonal, the counterset. And the action is ergodic. The ergodicity is defined like that.
Action of what? Not on. But it's a different space.
No, it is correct. Sorry? No.
So this is the relation between the first sentence and the second sentence of this theory. Preserves the maximal Euclidean subalgebra
Of ON.
of ON. Okay.
Of all, sorry, for all. For all. The maximal Euclidean subalgebra of OA.
Okay.
And in particular, in the setting of the full shifts, the action of the counterset, full shift, which is the enadic tree, the boundary of the enadic tree.
So this is a special maximal Euclidean subalgebra because it depends on the realization of this OA as a groupoid, état groupoid.
Not necessarily. No, not necessarily. You can also.
How unique is this maximal Euclidean subalgebra?
You can also view it as follows. So, like if you take.
What distinguishes this?
If you take on the generators, so you don't need to go to the groupoid of the generators. You can make sense of projections from here, where beta is any finite word, and then this will correspond to characteristic functions that the levels, the cylinder sets on which you construct the boundary. So it's quite canonical. And then you have a counterset, then this appears to be the first example of a compact matrix quantum group that acts ergodically on the counter space. And we were not looking for that, but it was showed up. And You do have other ergodic actions on ON. For instance, one has shown, like, for instance, that these acts ergodically on ON.
So sigma is the control set.
Yes, yes. Acts ergodically on ON, but this does not preserve the counter space. On the other hand, if you look at something that preserves the counter space, like the quantum permutation group, this cannot act ergodically because it can act ergodically only on finite many points. So this really seems to sit at the sweet spot to act ergodically in the counter space. And you cannot have such an action in the classical situation. So if you take a closed subgroup of UN, classical UN, it's a compact Lie group, it cannot act ergodically on a totally disconnected space because compact Lie group can have up to finite many components. So you really need to go quantum to find ergodic actions in the counter space.
So I would like to understand first the action of G1 infinity on ON. No, the first theorem.
I'm taking notes also.
Okay, the action of G1 infinity on ON is ergodic.
Yes.
Okay.
And
this action is given by phi. So
yes. And in particular, the action on the counter set is also ergodic.
No, and it's a Cuntz algebra.
Yes. ON is the Cuntz algebra. And
My goodness.
And yeah, we have several questions, like maybe we have time for questions to discuss. And thank you.
Ευχαριστώ πάρα πολύ.
Παρακαλώ.
Okay, are there any questions from the Zoom guys? Elmar, Young? Okay. I don't see any volunteers. Tomek?
I have a question about this gauge action.
Mm-hmm.
So this gauge action sits in classical isometry group.
The gauge action sits the classical isometry group. What do you mean? The gauge action sits inside the classical isometry group. Yes.
Can it be lifted to this
Everything.
quantum symmetry?
Yeah, it sits inside as well.
Also, yeah, because you have the map.
Yes.
But why it is contained?
So in here,
In this quantum group?
that's the classical one. Okay, let's take this for the full sheet.
Yeah, but okay. Now I'm speaking about
And this is inside
quantum groups. No, sorry, sister algebras of quantum groups. Because
yes, yeah.
so we have projection from functions onto functions on the unit circle.
Yeah. So you have, I have it here. Here. So you have the dual.
Mm-hmm.
You have the generators for.
What is the pre-image in these algebra functions on this universal quantum symmetry?
The gauge action,
which projects on this classical.
You just
function on the circle.
Yeah, you just take Uij to be the delta ij. The
Uij. So how this can cover all functions?
Just diagonal. Just diagonal. You see how this is generated? So you take these generators to be 0 if alpha is different than beta, and they're the same. You just put the empty.
So how can they cover all functions on the unit circle?
Because you also have them to be partial isometries. So then the circle will show up. It's not projections.
Okay.
They're unitized.
I would like to see some kind of symbol map, something like this. to obtain, in the quotient of this, to obtain these functions on the circle. But I'm trying to figure out what is this
I think
pre-image of this.
you just should
Under the projection.
a unitary here. Again, you.
Okay, so this
Some other unitary, yes.
okay, I see. So this is a diagonal.
Yes.
With some unitary.
Yeah, exactly.
And okay,
The same.
the same.
Yes, to get the circle.
Okay, perfect. Thank you. So this gives you this z function of the circle.
Yes,
Perfect. Thank you.
yes. And yeah, we have several questions like about how can one generate those groups. They're very canonical in the description, but it's very challenging for now to see how they're generated. Like, can be generated by quantumomorphisms and FN, for instance? Is there an example of where the quantumomorphisms of A is trivial, whereas this quantum isometry group is strictly greater than that because it always contains them? Or when can you say that thread stabilizes? Like what properties the matrix A should have so that this thread stabilizes? Can you deduce ergodicity for other cases except for the full shifts? It's quite challenging. We believe that if the matrix is quantum transitive, vertex transitive, then, or maybe some additional small property, it should be true, but it's not clear. The proof for the full shifts, it's already involved. And this is also interesting. You might think that the Cuntz algebra, something that everyone understands, has so much structure in it. It's interesting.
And how about K-theory of these quantum groups?
We don't know yet. I mean, this might come later on, I guess. But they are not amenable or combinable. I think they contain that. Yeah, I don't know. But yeah. But this should be also possible for other graphs, for other graphs that are algebras, but one needs to define this. The Log-Laplacian there and do the same. And it's not going to be easy because primitivity plays a role here because it gives rise to this Patterson-Sullivan measure. And you have a conformality and you have some tools to work with. Yes.
And what can you tell me about the sister algebras of these?
Not much at this point. Not much. That's what would you like?
Okay, let me tell you why I'm asking these questions, because we have one of these big open problems is when is a compact quantum group not contractible? This is a well-known result. In classical compact logical groups, the only contractible compact logical group is a triple. Okay? And in a number of cases, using K-theory, K1, and so on, we could prove that, okay, these compact quantum groups are not contractible. Definitely, it's like for free groups, okay? Reduced sister algebras of free groups. Immediately have abstraction, okay, the contractibility, and it works like a classical case. I think we can also say the same about deformation. Quantum groups, compact quantum groups.
But if they are,
it seems to me that is neither. So
if they are contractible, does it mean that all the subgroups should also be?
There is, I didn't think about this for a very long time. You see, this is part of our
Because this has quite many components, connect components. So I don't know if that would already obstruct.
I think it might be, yes.
Okay, so
because you see, this is contractibility is a very special case of our non-commutative Orsugulan type conjecture.
Why?
Wait, let me finish. it is a very, very, very special case, okay, when you take a sister algebra, the quantum group sister algebra itself, and you simply ask about a certain equivariant map from the sister algebra quantum group to the join of it with itself, which is really tantamount to contractibility of the group. And that's, as I said, a very special case, and we still don't know it for all possible complex quantum, just for some cases. But in general, I think that this non-completely possible lifetime conjecture is somehow anti-hereditary, but I would have to think about it to answer your question. But it's possible.
Okay.
That is okay. Yeah. Tomek, now go ahead.
So I have a little doubt. Why some subspace of a contractible space?
I don't know. No, I don't know. It's not true. Yes, but I don't know. Maybe it's different definition.
Because the subspace is not contractible.
Yes. Maybe it's a different definition. Yes.
I mean, yeah. I mean, for community systems, exactly contractibility of the nodes. To make sure that we are on the right page, we carefully define so-called unital contractibility.
Yes.
Because in sister algebras you can have different notions.
Yes.
Sister algebra is contractible, but
I didn't know the definition.
But it's somehow the usual definition. Okay. For example, you have a fun effect. The Teplin sister algebra, which you should think as a quantum disk, is not contractible. And the abstractions exactly have non-trivial projections, right? Nice Teplin projections, and they are elementary abstractions to contractibility. So I remember we had a fancy proof that the Teplin sister algebra is not contractible coming from our non-completely possible type considerations, and then somebody pointed to us, wait, but you can prove it directly from the definition, remembering that it had these non-trivial projections. Yes, you cannot kill one. Do that stuff. So, I mean, because you take like the unit of common and you need to have a rejection. It's like contractibility. Yeah. Okay. So, but there is some condition. I just don't remember which way that if it works for a quantum group, it cannot. It works for something of that sort. But like anti-hereditary, not hereditary, anti-hereditary. Because you see, in the formulation possible, we have a contradiction. It says that there does not exist such a non-existence claim.
Yes. Yeah.
So you have to be careful, with the logic. But there is something of that sort for subgroups. I just don't remember what, and let me not do it online.
Another question that I have is like, could it be true that if the thread does not stabilize, then you get ergodicity of the action? Stuff like that.
I have another very serious problem. I tried to look it up on the internet. So what is the status of Ariadne? Was she mortal or divine? Completely not certain. Well, it's discussed. You don't know if she was divine or mortal.
No, it's mortal.
Yes. Do you concur?
I this what I think. Yes. I'm not entirely sure, but I'm with Cuntz.
Princess.
Yeah.
Yes, I have a question. Classically, if you have ergodic action of a compact group, okay, then it is transitive. Which means that your space is
C-star ergodic. C-star ergodic.
Yes.
Not
for continuous functions.
yes.
But this
I'm
is
with
about
you. Yeah. Yes.
Yeah, but I'm talking about classical space.
Yeah.
Yeah, but you should specify which algebras you use.
Transitive. Yes.
Yes. Also, you can think about the homogeneous space.
Yes.
Do you have in your examples of ergodic actions of your compact groups homogeneous spaces? But quantum homogeneous spaces.
These are. But they cannot be classically.
Yes, of course. But it's homogeneous space. Quantum homogeneous space.
isn't it defined as having an ergodic action, or do you need something additional?
Remember, additional types of homogeneous spaces. Quotient homogeneous spaces.
Exactly. But it's a different story, because there's this funny fact, as was studied by Podleś, that even though we have this ergodic action, this need not be a subalgebra of your.
It's not a quotient type.
It's not the quotient type. This is why when he was classifying, homogeneous spaces for SCP2 to find his quantum spheres, he also found matrices are also quantum spheres in the sense of, but they are not embeddable. They are not subalgebras of quantum. So yeah, in general, but this is a completely quantum subtlety. If you take sister algebras and they are commutative, then ergodic means transitive. So.
Yeah.
There is homogeneous space of a quotient type.
Yeah, so that's a well-posed question.
Yes. Maybe. There are several questions to ask. It's already
very interesting, because
it's already
Cantor said. Yeah. Okay, it's very.
Yeah. I also
want to classify non-homogeneous.
Yes, exactly.
If quantum speaking, it is a homogeneous.
It's a good selling point. Yeah.
Wonderful.
Yes. Yeah. Probably in some definition it is. Yeah. But you have the main ingredient there with this thing. So I bet it is.
And I understand that this action is very far from being free.
We haven't checked this.
Well, because you have ergodic and free, and it's a Galois object. It's almost the same.
Yeah.
Classical torus and quantum torus.
Yes.
Classical torus.
Yes, you're right.
Torus, and this is a Galois object. It's ergodic and it's free.
Yes.
So it's very far.
No, I agree.
So classifying stabilizers.
Yeah, exactly.
I'm happy.
That's what I'm
happy. Yes. I'm happy that you come up with several questions that can lead to projects. I think I succeeded on that.
Yes.
So many questions to ask.
So either there's only one orbit and one stabilizer, or maybe if it's not of this quotient type, there could be some
Could be
hierarchy of points of a Cantor set classified by properties of this action.
Yes. But I think we should stop.
Yeah.
For the time being. So let us have Harry Starr, our speaker again. Thank you so much.
I don't think so. Dziękuję bardzo.
So this sounds very deep.
Thank you.